In part A, we did problems like the square root of 4 is the number I need to square to get 4, 2. And 2 was a nice, even, whole number answer, an integer. Sometimes, though, we get problems like this. What's the square root of 12? Well, 12 can be written as 4 times 3. And it turns out that I'm allowed to take the square root of a product and rewrite it as the product of two square roots. In other words, I can split up what's inside the square root if it's a product, not if it's a sum, and rewrite it. Once I've done that, I can rewrite this product, one number times another, as the square root of 4, which I know is 2, times the square root of 3, which doesn't have a perfect square root. In the same way that when I have a product like 2 times x, I tend just to write 2x, I can rewrite this without the dot as well and just write 2 times the square root of 3. Another way to think of 2x is as 2 x's. The thing I have is x's, and the number of them that I have is 2. I have 2 x's. Here, the thing I have is square roots of 3, and I have 2 of them. So I have 2 square roots of 3. And you'll often hear this read that way, 2 square roots of 3, or even 2 roots of 3. Just like we don't write a 2 if the root that we're taking is the square root. If I just talk about the root of a number, I mean the square root. So you might hear me call this 2 root 3, or 2 square root 3, or 2 roots of 3. What I mean is 2 times the square root of 3. This is the simplified form of the square root of 12. Let's do another example. The square root of 75. What number do I have to square to get 75? There is no integer that I can square to get 75, but I can rewrite the square root of 75 as the square root of 25 times 3. Because I now have a product inside my square root, I can break the square root up into a product. 25 goes here, and 3 goes here. Now I'll rewrite my product as the square root of 25, which I know to be 5, times the square root of 3, which doesn't simplify. And that can be written as 5 times the square root of 3, or 5 root 3. Let's simplify the square root of 18. Can you think of a way to write 18 as a number times a number, a product, where one of those numbers is a perfect square? I could write 18 as 6 times 3, but 6 is not a square and 3 is not a square. I could write 18 as 9 times 2. 9 is a perfect square. 3 squared will give me 9. So rewrite 18 as 9 times 2. Split up your square root into the product of 2 square roots. Rewrite your product by evaluating the first square root. And finally, tidy up your answer. You don't need the dot. The square root of 18 can be simplified. 3 roots of 2, or 3 root 2. What about a number like 240? How can we rewrite the square root of 240? It's not as easy to see what the two numbers might be that I can multiply together, where the first one is a perfect square. It's not even obvious whether we have a perfect square as a part of the number 240. So before I begin, I want to see if I can find a way to write 240 as a product. So I'm going to make a factor tree and see if I can find a pair of numbers that are the same. Let's do 10 times 24. And then 10 breaks down to 2 times 5. 24 is 3 times 8, or 4 times 6, or 2 times 12. 8 is 4 times 2. 4 is 2 times 2. If I go back and circle all my prime roots, then I can see that one way to write 240 would be 2 times 2 times 2 times 2, finding all the 2's, times 3 times 5. And I've found not only one pair of numbers, but another pair as well. So one way to write 240 is 4 times 4 times 3 times 5. Why did I multiply these and not these? I was looking for pairs of numbers because 2 times 2 is 2 squared, or 2 times 2 is 4. Since I can write the square root of a product as the product of square roots, I can rewrite the square root of 240 like this. Then when I go to do my multiplication, I can change this square root of 4 to 2, this square root of 4 to 2, this square root of 3 cannot be simplified, and the square root of 5 cannot be simplified. Now I can do this multiplication, and if I can break up a product, I can also put it back together. In my last step, I'll rewrite the 4, leave the dot off, and do the multiplication, 3 times 5. The square root of 240 can be simplified to 4 roots of 15. 15 seems like a big number, but its only factors are 3 and 5. It doesn't break down into a perfect square times something else. This is as far as I can take it. We did a problem like this in Part A as well. Remember that I said that the square root of a fraction is the fraction that I need to multiply by itself 2 times to get the original fraction. This can be written as the square root of 9/6 squared. Squaring and unsquaring cancel each other out. So I get just 9/6. Of course, this can be simplified or reduced. So my final answer here is 3/2. Instead of that approach, what if I took the square root of 81/36 and rewrote it as 2 separate square roots, one over the other? The square root of 81, sitting by itself now in the top of this fraction, is 9. And the square root of 36 is 6. That's what I got here. I can reduce this fraction because I could reduce it in the previous example. So it turns out that I can split a square root up not only if it's a product, but also if it's a quotient, a fraction. Let's do an example where the answer may not be an integer over an integer. This is the square root of a fraction. So the first thing I might want to do is split my square root up into the square root of the numerator over the square root of the denominator. The square root of 169 is 13, an integer, but the square root of 108 is not a whole number. So I need to figure out how else I can write 108. 2 goes into 108 54 times. 2 goes into 54 27 times. 3 goes into 27 9 times. And 3 times 3 is 9. I'm circling my prime roots, and I can now make the observation that 108 can be written as 2 times 2 times 3 times 3 times 3. If 108 can be written this way, then the square root of 108 can be written as the square root of this product. Notice that I have a pair of 2's, so I can bring 1 outside, and a pair of 3's, so I can bring 1 outside. This 3 does not have a pair or a partner, so it stays inside the square root. The square root of 108 can be simplified to 6 root 3. This can be written this way. This was just scratch work. So in place of root 108, I'm going to write 6 root 3. The square root of 108 over 69 can be simplified as 6 root 3 over 13. This problem asks you to simplify -5 times the square root of 162. There's no dot here, but multiplication is implied. I can simplify the square root of 162. So what I'm going to do is treat this as two separate problems, at least at this point. Whatever I get by simplifying the square root of 162, I need to multiply that by -5. Let's do this piece. Since 162 can be written as 2 times 81, and 81 can be written as 9 times 9, and each 9 can be written as 3 times 3, I can write 162 as 2 times 3 times 3 times 3 times 3. If 162 can be written as this product, then the square root of 162 is the square root of that product. But the square root of this product contains some pairs. I could rewrite this as the square root of 2 times 9 times 9. This can be written root 2 times root 9 times root 9. And that can be written as the square root of 2 times 3 times 3. This 3 times 3 here is 9, and the square root of 2 doesn't simplify. The square root of 162 can be written as 9 root 2. So I'm going to replace root 162 with 9 root 2. Without writing the parentheses, because I simplified this as one big piece, it's as though I wrote -5 times the quantity 9 root 2. Now, using the associative property of multiplication, I can rewrite the problem this way. And then, doing this multiplication, I get -45 times the square root of 2, or just -45 root 2. -5 times the square root of 162 can be simplified as -45 times the square root of 2.